So like I was saying, right? So that was for part 2, right? So moving on to part 3, right? Explain the forward error correction scheme with an applicable example, right? So forward error correction is a mechanism which is used by the sender in order to tackle transmission errors due to the channel. The sender adds redundant data in the signal being sent so that the receiver can detect and correct errors, right, within a reasonable bound, and does not need to ask the receiver to send the data again. Such techniques can be used in satellite communication where retransmission could be a real pain as the distances are huge. So you might have done something on error correction in CS211. Have you guys done something in something regarding error correction in CS211 or in your CS units? Have you guys done something on error correction? I believe there was a concept that was taught in CS units. You remember that? Guys, do you remember that? Okay, so Zayul remembers that. What about William? Do you remember that?
Yes, I remember.
Okay, just in case if you have forgotten, I mean, I don't want you guys to remember the whole method. I'm just asking, do you remember, like, just that basic concept, like, we add something to our number of bits, right? And we send it out to the user or the receiver at the other end. So what happens is that particular bit encrypts our code or encrypts our data, as well as it protects the external noises disrupting our signal or some sort of error occurring in that particular signal, so that the receiver does some sort of error correction to receive the signal. You might have learned that basic idea. Okay, so this is the same thing, right? So forward error correction is something that it is just basically saying that when you forward your signal, or when you are trying to send out your message, you add an extra bit, or you add some sort of extra redundant data to your message signal, right? So that when your receiver gets that particular signal or that particular message, he or she can compute the reverse or do some sort of computation on that particular message signal that he or she receives to retrieve the original signal back, right? So in that particular case, what happens is that the sender does not have to resend the signal, right? There's some sort of privacy part also embedded in that, but at the same time, the data or the message signal that is being sent is protected from the external noise or external disruptions that can actually change the message signal, right? So a satellite communication is a good example over here in this particular case, right? So if you're trying to receive signal from the satellite, right, back to the earth, so it will take some time, isn't it? So we want to protect the data, right? So as it comes through, we want to add that error correction of forward error correction technique or scheme to be added over there, so that once we receive the signal, we can do some mathematical computation or some sort of computation in order to receive the original message, right? So that the satellite does not have to resend the message. So when we mean by forward error correction, so the error correction is basically done at the sending point, right? So we add extra set of redundant data before we send the message out, right? So that is forward error correction, right? So all of you are okay with this? Part 3?
Yes.
Okay. Question number 4. What are the advantages and disadvantages of spread spectrum techniques, right? So spread spectrum techniques, right? So let me just show you what is spread spectrum. spread spectrum is this, right? So we have a signal, right? Let's take this as an example. So we have a signal, right? We have a signal that has a narrow bandwidth, right? At the moment, we have a signal that has narrow bandwidth, but has high transmitting power, right? But what happens is when we are transmitting a certain sets of frequencies are corrupted, right? When we have a narrow bandwidth, when there is a noise, it just corrupts one set of frequency, right? And the bandwidth is not large as well, right? So large sets of frequencies cannot be catered for, right? Or large sets of users cannot be catered for in this particular case, right? So what does a spread spectrum do? It basically reduces the transmitting power and distributes it to other frequency, right? So what happens is this same message signal is now redistributed at a wider set of frequencies, right? So you can see the bandwidth was from here to here. Now the bandwidth has increased from here to here just by redistributing this power, this same transmitting power over different sets of frequency, right? So when this happens is that if there is, like if there is some sort of error occurring in one or two frequencies over here, it is not going to affect the whole message signal or the whole what do you say, the whole data that is being transmitted, right? So some of the advantages of that spread spectrum technique is that it provides some sort of privacy via the use of random codes, right? So this random codes is what we use to redistribute this same message signal, right? These random codes or pseudo codes that we use, right? Pseudo random codes. It is what is used to redistribute this particular value, this particular peak, the peak power to be distributed over different or vast range of frequencies, right? So if you want to learn more about spread spectrum, you can search your YouTube videos for that, right? So there's some good examples that are on YouTube, so you can always learn more on spread spectrum through that, right? So one is the privacy, right? When you are using a set of random codes, you protect your data sets, right? You also gain immunity from various kinds of noise and multipath distortions. Like I said, if you distribute it through a number of frequencies, right? When you increase your bandwidth, more sets of frequencies are in now being accounted for, isn't it? So if there is one set of frequency distorted or one set of extra set of noise distorting a certain frequency power, right? What happens is that does not affect the whole signal that you are basically broadcasting, right? It does not affect the main signal or the main message signal, right? In that particular case. So basically it gains immunity from various kinds of noise. Share the same bandwidth with multiple users, right? So as the bandwidth increases, the number of users also increases, right? So your ability to cater for different users also increases, right? Okay, because you are accounting for different frequencies, right? Now, so there can be you can share the same bandwidth with multiple users, right? Disadvantages, it's complex implementation, right? When you are adding pseudo random codes, right, there's some sort of computation that needs to be done, isn't it? So when you are doing that, the complexity of that particular message or the complexity in order to implement that particular spread spectrum technique becomes complicated, right? And then if you are increasing the bandwidth, the number of bandwidths, and you are not, no, you are having a small set of users, right? So you are now redistributing the same message signal, like I showed you, right? The same message signal over a wider set of frequencies, isn't it? So now when you are using the same, now once you are spreading that over a different range of frequencies, now what happens is that the number of users need to be large, right? When you are increasing the bandwidth, the more users, the more utilization of that same, the large bandwidth that you have, you can utilize it much more better, right? If you have one or two users in that same particular bandwidth, what happens is that the efficiency or the number of the inefficiency of the bandwidth increases, right? Or the bandwidth is not basically being used or utilized to its maximum potential, right? Okay. and it can lead to maybe like some sort of losses as well, right? I mean, like from a business point of view, if you don't utilize that particular technique to its maximum ability, you are basically making some losses in that particular case, right? You are um, basically losing out on different different sets of frequencies in this particular case as well, right? So all of you are okay with spread spectrum? No? All of you understand what spread spectrum is? Okay. So have you gone through spread spectrum in your lecture notes? Okay. Look, there is different ways to explain this communication signal, right? This is something related to your DSP, right? Okay. Okay, that's great then. There's different ways to explain spread spectrum. In fact, there's different explanations to each and every, you can remember these communication lines into different ways, right? There's no fixed, I mean, there's no fixed definitions to everything, right? So it's just how you picture things, right? Um, so I might be explaining differently compared to different things. You find, like whatever suits your need, you go and use that, right? Or you utilize that as, that resource as per your understanding. Remember, this course uses a lot of OERs, or open education resources. So you guys are always welcome to go out and do your own research and to get a better understanding of all this information there, right? Okay. Moving on to problem number 4, right? Problem number 4 again. Problem number 4 is consider communication system operating in the 5.9 gigahertz band, assuming the free space loss model for signal attenuation. The gain of both the transmitting and the receiving antenna to be 1 decibel and a noise level of negative 85 decibel dBm, right? Decibel milli, right? Or dBm. Calculate the range of communication if the transmission power is 100 millivolts. So you can see your receiving power is basically in dB. Your antenna gains are in dB, right? Isn't it? So the first thing first, what is the formula for free space loss model? It is basically given by the receiving power divided by transmitting power, right? Which is basically equal to gain, the transmitter gain times receiver gain times the wavelength squared holding upon 4 pi d squared, right? So this is basically the formula of the free space loss model, right? Or the free space loss model just basically states that the loss of power when you are transmitting in an open space without any losses or any obstacle in that particular path, right? There's some losses in that particular case. So that is the free space loss model, right? So you have you have a transmitter here, you have a receiver here. Let's say you have a receiver here and there is no obstacle. So this particular path is a free space. And in this particular free space, the loss that you have is this free space loss model, right? So basically, if we are talking about the free space loss model, what is the power? The power difference that is being caused as the signal is being transmitted from the receiver end to the transmitter end, right? So you have done this in your lab, so I believe you do understand what a free space loss model is, right? So there's other forms of this free space loss model formulas, right? So let me just quickly show you that. Free space loss formula. Wait. There's actually a particular formula over here. I had it yesterday, but I lost it. So this is why I have to search again. Using Google. Yeah. Effective area. I think is okay. We have this particular free space loss model formula, right? So like I was saying, right? Free space loss accounting for gain of other antennas, right? So basically, free loss formula is the power transmitted divided by the receiving power, right? So, so it is vice versa what we have over here in our formula, right? So, the original formula is actually in terms of gain, right? So you can replace this gain with effective area, right? Okay, you can rewrite this, right? The same formula in terms of effective area. So your job in your lab was to actually replace the effective area, right? Different antennas have different effective areas. So there's 3 types of antennas, right? Like I said, or like you have already noted, these 3 types are isotropic, dipole, and the other one is parabolic, right? So each of these antennas have different effective areas. So you had to go over those, right? So that made up the three free space loss model for 3 different antennas, right? So that was just an explanation going back to your labs, right? So based on this, right? So going back to our question, the range of communication if the transmission power is 100 milliwatts, right? So using this particular formula over here, what we need to do is we can see that our noise level is in terms of dBm. Our antenna gain is in dB, so we need to convert this into dBm, and we can convert our power directly to dBm, right? So basically taking 10 log of this particular value will give us our dBm value, right? So converting this into dBm is basically 10 log of base 10, right? Of 100 times 0.001. Okay. So we get a dBm value of 20, right? Okay. So we get a dBm value of 20 in this particular case. So so since we have converted our transmitting power to dBm, right? We have our receiving antenna power as negative 85 dBm, right? Now what we need to do is to convert our, no, we can use this, right? dBm. We can use this as it is, right? The antenna and the frequency gains in terms of dB, right? So we consider that we are able to decode the receiving power must be less than equal to the noise level. So we consider that. Okay, the receiving power has to be less than the equal to. So this is what we are considering, right? Set. So this is just a consideration note, right? Based on this, what we can do is we can also what can we do? Oh, we can find our lambda, right? So we know our gain. We know our gain over here as well, right? The gains are 1, right? So gain is 1 in both the cases. We know our transmitting power. We know our receiving power, right? Our receiving power and our transmitting power. What else do we need? We need to know our lambda, right? So lambda is basically equal to speed of light divided by frequency. So in order to find our lambda, so our frequency is already given in our question, that is 5.9 gigahertz, right? So taking this particular value and taking the speed of light, we can find our lambda. So our lambda is basically equal to 0.051 approximately, right? Okay. Now what we can do is we have now all our values in dBm, and we have our what else? We have our lambda, right? Our lambda is in our standard units, right? Okay. So now what we need to do is take the log of both the sides, right? If we take the log of both the sides, so this will read as the log of receiving power minus log of the transmitting power is equal to gain plus, log of gain plus log of receiving power plus the log of this particular value, lambda squared, or basically plus 2 log lambda, right? And minus 4 times pi times d squared. So bringing 2 in front, right? I believe all of you can, all of you know the log properties, isn't it? Using the log properties, we can rewrite the same equation over here, right? What we have as this, right? Okay. So now we have our log equation, right? And we have all our values in dB. So basically what that means is all our values are in dBm, right? Okay. So when we take the log of this particular receiving power, we are basically writing the dBm value, right? Like taking the log of this transmitting power, we have dBm value, right? Okay. And then taking the log of dB is again as it is, right? The log of this transmitter gain is 1 dB. The log of the receiving gain is 1 dB again, right? So based on that, if we evaluate our formula, right, taking these particular values, our transmitting power to be 20 dBm, our receiving power to be minus 85 dBm, right? And our antenna gains to be 1 dB, right? 1 dB. And taking our lambda to be equal to 0.051, right? Approximately. And substituting it into the main formula, we get our distance is equal to 908 meters. So I want you guys to try this out right now, right? I want you guys to try it out. Do you get the same value? Are you guys going to get the same value? Just check. Guys, are we going to get the same value? You know why we are not changing the gain values over here? I mean the units of this gain over here. You know why? Why we didn't substitute it into dBm? Okay, you can see these particular terms over here, right? The receiving power is upon the transmitting power, isn't it? So if we are using whatever unit we are using for our power, the receiving power and the transmitting power, it has to be same, right? Because the units will cancel itself off. Okay, the units of this receiving power is going to cancel off with the transmitting power, isn't it? Now we have to know this, right? Over here, the gain unit is not being cancelled out by anything, right? So whatever we have to use it in the standard unit, okay? But for the receiving power and the transmitting power, the units will be cancelled off, okay? So that is why we have to ensure whatever unit we are using for the receiving power, the transmitting power should also have the same unit. So you get this part? We do not need to do anything with this because the units of these two will cancel itself off. Are you getting this? Okay. So that is why we have to ensure, right? Okay. So that is why we had to change the unit of these two, right? Because eventually the units of these two will cancel itself off. So we have to ensure these two are in the same units, right? So if we were using the standard rules, so if we are using a milliwatt power transfer for the for PT value over here, so we have to ensure that our receiving power is also in milliwatts. Okay. Anyways, So that is why we are converting this receiving power and the transmitting power into same units, right? Okay. Now, this transmitting gain, we can use it as it is, right? And this lambda value, we have to find our lambda from this particular formula over here, that is speed of light divided by frequency. Okay. And this particular part is as it is because we know our distance, we are calculating our distance, right? So what we can do is take the log of this, right? If you take the log of this whole formula, you are going to basically get log of PR, right? So PR upon PT, which is equal to log of, let's take 10 log in both the sides, right? 10 log of this whole term over here, this term over here, which I'm going to call as A. Okay. Now what we can do is further expand this, right? We can further expand this. I'm just going to show you for this particular part over here, this one. We can rewrite it as 10. I mean, if we are taking 10 log of this, so it is basically 10 log the receiving power minus PT, isn't it? Right? For this over here, because if we are dividing, we minus. So it is, sorry, it is 10 log. Sorry, I have to erase this. Okay, it is minus 10 log PR minus 10, sorry, 10 log PT, right? Okay. So when we are taking 10 log of this, right? When we are taking 10 log of it, we are basically converting whatever value we have or the unit of this power that we are having in terms of dB, right? Okay, dB or dBm, right? So we are basically converting into decibels. So that is why we this is where our decibels have come in, right? Our dB values have come in. Okay, and then if we take this the 10 log of this K, we are basically using the dB unit. So that is why it is in dB, right? dB, and if you are multiplying, it has to be plus. So whatever gain we have in dB plus gain of this receiving end in dB plus this 2 will be multiplied by the power in front, right? Using the log definition, you can expand this and you'll find the distance to be equivalent to be 908 meters, right? I want all of you to solve this and reach out to me next week, right? Okay. During the lab, I'll ask you again because this is really important, right? Anyways, using the logarithmic formula, you can expand this, right? And then the transmission power, if you want to communicate the range of 3 kilometers, right? If you want to calculate the transmission power for the range of 3 kilometers, so what happens is that in this particular case, using the same particular formula that you have over here, right? The same particular formula you have over here, in place of transmitting power, you are our transmitting power will be unknown in this particular case. We know our distance, right? We know our distance. So in this particular formula, our distance was unknown, right? In the first, I mean, this particular formula that we have over here. Now what will happen is, now in this particular case, our transmitting power will be unknown and we just need to solve for our transmitting power, right? Whatever values we have, we keep it same, right? That we used for this solution, I mean, part 1, right? We use the same particular values over here in this particular formula that we have derived over here, but we solve for our transmitting power and we'll find that our transmitting power is basically equal to 1 watt, right? It's basically equal to 1 watt. And remember, the distance value that you'll be using will be in terms of meters, right? So basically you'll write as it is, right? And then you just have to take the receiving power and take it to the other side, right? It will become minus the receiving power. And then you just have to take the negative on both the sides to find our transmitting power, right? So our transmitting power that we will be getting through this particular formula, it will be in dBm. We just need to convert it back to dB, I mean, in watts, right? So if you convert the transmitting power to watts, you should be getting 1 watt. Question number 3, what would happen if the frequency was 900 megahertz, right? So again, We know our frequency, we know our lambda. We are just need to find our distance, right? So remember, it says what will happen if the frequency was 900 hertz. If you go back to question number 1, right? If you go back to question number 1, in place of 5.9 gigahertz, we change this 5.9 megahertz into 900 megahertz, right? And what we do is reevaluate the distance, right? We reevaluate the same formula. In place of 5.9, we use 900, right? 900 megahertz. In place of 5.9 gigahertz, we use 900 megahertz in order to find our distance. So you'll find your distance to be equivalent to 5,932 approximately, right? In the questions below, please provide true or false for the statements and justify your answer with proper arguments. Data throughput is same as the modulation rate of the signal. Data throughput is not the same as your modulation rate, right? So data throughput is the data rate that we are talking about. The data rate is not same as the sampling rate or the modulation rate, isn't it? You might have learned this in 2 to 5. The sampling rate is different from the data rate, right? Or the signal rate, right? Okay, so you can go through the explanation over here. Part 2, it says in modeling a signal wireless communication system in which two nodes are in urban scenario with no line of sight path, additive wide Gaussian noise channel model is a good guide for the designer. No, right? When we are talking about additive wide Gaussian noise channel, we are basically talking about the model having external disturbances from or having external disturbances due to thermal energy or having some sort of noise being added to that particular signal, right? You are adding something, right? So it is basically a noise analyzing model, right? It is not going to be taking into account of any disturbances caused, right? Or it is not going to be considering any, it won't be considering the line of sight paths, right? So in this particular case, the Rayleigh's channel model is going to be sufficient, right? So I want you guys to go over this additive wide Gaussian noise and the Rayleigh's channel model, right? So I want you to go over those two. Frequency diversity is achieved by spreading the signal in time by sending multiple copies of the signal at different time instances. No. This diversity means what do you say? Frequency multiplexing, right? So when we are meaning by frequency diversity, we are basically spreading the signal over different frequencies. Okay. When we are dealing with time, we are basically spreading the signal upon different times, right? So basically, if it says frequency diversity is achieved by spreading the signal in time by sending multiple copies of the signal at different rates and at different time instances, no, this is false, right? When we are this particular statement is true for time diversity, right? It is not true for frequency diversity. If we are talking about frequency diversity, it is basically spreading the same signal over multiple frequencies, okay, at different frequency instances, right? Multiple path propagation always improves the SNR. No, it is not always true, right? When we have multiple paths, if we have 2 or 3 signals, right? Remember, I showed you the multipath propagation. Remember, what happens is that when we are talking about the signal hitting a disturbance, right? Hitting a particular building and coming back, that hitting, that obstacle can change the phase of that particular signal, right? So what happens is by the time it reaches the receiver, if the signal is out of phase, it will cancel itself off, isn't it? It will cause a non-constructive signal at that particular point, isn't it? Or if both the signals are in phase, it will cause a constructive interference, isn't it? So in both the cases, multipath propagation does not always improve the SNR, right? So basically, whenever we have 2 signals arriving at this receiver and in phase, it is going to cause a constructive interference, which is going to improve the signal to noise ratio. But if 2 signals arrive at the same destination out of phase, it will cause a non-constructive interference. So the signal will cancel itself off. So it is both likely, right? It can improve, it can also degrade the SNR value, right? So it is false. It does not always improve the SNR value, right? You can go over the definition over here. So anyone has any specific question, right? I want you guys to go over this calculation, right? This calculation part is really important. And I want you guys to raise any queries regarding this particular calculation, right? Okay. If not, we'll redo this, right? We'll redo the communication, I mean, these calculations, right? Okay, this could be tested in your exams. I have taken a lot of time, so that is why I had to speed through. I couldn't solve this, right? So we'll try to solve this in the lab, right, next week. Or we try to come back next week and we'll try to solve this, right? But in the meantime, I want you guys to solve it. If you guys are able to solve it, then that is fine. We don't need to discuss it, right? So thank you for joining in, right? So I'll see you next week, right? If you have any queries, you can ask me right now. We have 2 minutes before this session ends. Do you guys have any queries? Okay, right. So then see you next week, right? Thank you for joining in. I'll end the session over here. Thank you.